Okay, now till now in the earlier sessions we have been talking about light, what light rays is, are what are the optical fibers and what are how the optical sensors are working and what are the various properties of light, etc., etc. Now in that domain itself, there is a very important phenomena that we are going to study in this session that is called light scattering. Okay, this particular thing is very important when it comes to finding out the chemical compositions of certain solutions where which involves macromolecules. Okay, so we need light scattering, which is the actual technique called dynamic light scattering, that is DLS technique, is actually a very important technique which helps us in finding out the macromolecules, the size of the macromolecules we can find out with the help of the light scattering technique. So we let us understand what actually scattering means. Now, scattering is a general physical process where some form of radiation, such as light, sound, or moving particles, they are forced to deviate from a straight trajectory by one or more paths due to localized non-uniformities in the medium through which they are passing. Okay, so it looks like a very complicated thing. Very simple words that whenever you are passing light through a medium, it is supposed to follow some path. We all know that light travels in a straight line. Okay, unless it gets reflected or it gets deviated from some surface by reflection or refraction or something like that. So basically, when the light, there is a random change in the light path of the light, the trajectory that it is supposed to follow, when that changes very randomly due to some non-uniformities that are present in the medium, it is called scattering. Okay, if you have simple plain, a very common example is if you have plain water. Okay, you incident light into it, it will get a little refracted, but it will follow some straight trajectory which it is theoretically which it is supposed to follow. But at the same time, if you take water which is full of mud, okay, and then in that if you try to incident light, then the light will not follow any particular proper trajectory. All the light rays will be going here and there, and it will be scattering about. The reason is that the mud particles, that the sand particles that are present in the water, they are actually acting as non-uniformities which are deflecting the light rays here and there. So such a phenomena is what is called scattering, right? Right. So in conventional use, this also includes the deviation of reflected radiation from the angle predicted by the law of reflection. That means if there is total randomness, reflection also is taking place, but not as per the law of reflection. Okay, then that is also part of scattering. Reflections that undergo scattering are often called diffuse reflections, and the unscattered reflections, they are called specular reflections or the mirror like. So if there is a reflection taking place in clean water, it is called specular reflection or a mirror like reflection, which is according to the laws of light. Okay, laws of reflection and Snell's law and all that, whatever we follow. So that is called a specular reflection. At the same time, if you have a muddy water, and in that if you try to measure the reflections, those scattered reflections, they are called diffuse reflections, right? So scattering may also refer to particle-particle collision between molecules, atoms, electrons, photons, and other particles. Okay, so of course, when I say randomness, when there is random scattering, why that is taking place? Because when you add mud, if you have seen the mud particles, they themselves are following a very random movement in the water, and that is, subsequently giving rise to scattered reflections of light. The types of non-uniformities which can cause scattering, they are sometimes known as scatterers or scattering centers. They are particles, bubbles, droplets, density fluctuations in fluids, crystallites in the polycrystalline solids, defects in monocrystalline solids, surface roughness, cells in organisms, or textile fibers in clothing. All these small, they are not micro, but they are macromolecules which are present in any solution, and they are showing some random movement, because of which the light, when it falls on that solution, it gets scattered away. So these non-uniformities, the mud particles, or maybe maybe some soap bubbles are coming in between. Okay, all these are called scattering centers or scatterers, which are actually the non-uniformities in a particular solution or a fluid, and which are causing the light to scatter. Okay, now this particular scattering property we use in a very important technique called dynamic light scattering. So dynamic, or DLS, it is a technique in physics that can be used to determine the size distribution profile of small particles in suspension or polymers in solution. Okay, now we have to keep in mind, these are those particles which do not get dissolved. Suspension over here is a very important word. We are not talking of solutions in which 100% dissolving is there. Okay, these are not microparticles. These are not atomic particles. These are macro particles or small particles which remain suspended when you put them in some fluid or water or any solution. Okay, in the scope of DLS, the temporal fluctuations are usually analyzed by the means of intensity of photon autocorrelation function, which is also known as photon correlation spectroscopy or quasi-elastic light scattering. Okay, so it's a technique. We'll just go through how it works. It's a technique in which the light rays are actually used to find out the size distribution profile. Now, size distribution profile basically means we need to find out, if we have a suspension which has many particles hanging around in it, we want to find out what is the size of these particles which is hanging in the solution. Does the solution has particles of only one size, or does it have different sizes? That is called size profile, size distribution profile. Okay, so all that kind of thing we can find out with the help of um, dynamic light scattering technique. And in biomedical also, it is very important, because protein fluids and all that, these are very common in uh, human body. So many fluids we have, in which we have proteins, we have other macro molecules involved. So you can actually find out the size distribution profile of body fluids, and you can find out, is there anything abnormal going on. Like, cataract sensing is one of the very important applications of DLS, because your eye fluid, if it starts having an aggregation or a coagulation of protein molecules, that is actually, some abnormality. It starts showing when you use DLS technique. The molecules, when they aggregate, they coagulate with each other, they become quite large, and so they start showing, dynamic light scattering. They start showing scattering. So that technique we can actually use to find out what size my molecules are present in the eye fluid. If a larger size is being sensed or detected, that means the cataract has started coming in the eye lens. Okay, so likewise, DLS is a very important technique that we can use these days in biomedical applications. So now, when in a solution, macromolecules, when they are present in a solution, they show random motion called Brownian motion. Okay, a monochromatic light source, usually we use laser in this. When it is shot through a polarizer into the sample, the scattered light goes through another polarizer, where it is collected with the help of a photomultiplier, and the resulting image is projected on the screen. This is called speckle pattern. Okay, now over here, we have to see over here is that, when you're using a monochromatic light, you allow the light to fall on the, I'll show you the arrangement. This is what it looks like. You have a sample in between which has some macromolecules, and the macromolecules are actually showing very random Brownian motion in the solution. Okay, now from one side we have a light source, which is usually laser. Okay, we incident that light. Now the light gets scattered with the help of when it gets collides with so many macromolecules, and those molecules are also constantly in motion. So what happens, it gets scattered, and at the other end we have a photodetector We keep changing the angle. You can see theta is shown over here. We keep changing the position of this photo detector, and we, at different angles we measure, we catch this light, and we try to see what kind of pattern is detected. And this particular pattern which this photo detector is actually catching, we when we you display it at a screen, you get a pattern which is made up of small black and white spots. Okay, like you can see on your screen at the right bottom, this particular pattern that you see, this is what a laser speckle pattern actually looks like. It looks like as if, on a white sheet you have randomly thrown some uh, black pepper particles. So this is what a speckle pattern looks like. Basically, is in this particular arrangement that you see, the photo detector, what it is capturing, if you try to put it on a screen, maybe with the help of a projector or something, if you see it on the screen, this is what it will actually show you. This kind of a pattern it is going to show you. This is because of that random reflections and refractions and scattering. Basically, I should now use the word, basically because of that random scattering of light that is taking place. Now, why these black and white patterns they are coming in? As the light scatters from the moving macro particles, the motion this imparts randomness to the phase of the light that is being scattered. So, such that when the scattered light from two or more particles is added together, they will be changing destructive or constructive interference. So, what happens is when the light, because it's all random, all the macromolecules they are moving very randomly. So, the light rays striking from them, they are also getting scattered randomly. In this randomness, what happens is at some places the light rays they get added up in constructive interference, or in some places it gets added up in destructive interference. That is, the two light rays which are in the same phase, when they get added up, it creates a bright spot which you see as a white color in that speckle pattern. But if two light rays which are opposite in phase to each other, when they get added up, it shows you a black spot on the screen, because the intensity gets cancelled out, and on the screen you can see black spot. So this white and black random spots that you see in the speckle pattern, this is because of the random constructive and destructive interference of the light rays that is being scattered from the random moving macromolecules of the solution. Okay, so I hope you get a wholesome picture now, that you have a solution. In that solution, you have macromolecules present. These macromolecules, since they are large in size, they show random Brownian motion. From one side, we have a laser source. This laser light source, when the light is incident on the solution, the light rays, it strikes these randomly moving particles and gets scattered around. This scattering is actually collected with the help of a photo detector, and when you see it on the screen, you see it something called a speckle pattern, which is a combination of black and white spots. And this black and white spot actually is arising due to a constructive and destructive interference of the light rays amongst each other. Okay, and this is this pattern is not constant. It is a time dependent fluctuation. At every time instant, if you see at the very next second, it will be black and white spot, but again it will be very random. At the same point, at time instant 1, if you were having a black spot, next time instant what you will have, you don't know. It might be white, it might be black, because it's total randomness. So this speckle pattern that you're seeing is basically time dependent fluctuation of intensity of the scattered light. Okay, and these fluctuations, they are measured by with the help of a very fast photon counter. So how this fluctuation is taking place, that we count with the help of a photo counter. Okay, now just to understand how we are going to proceed further, the fluctuations that are taking place over here, that how fast or how slow the fluctuation is taking place actually depends upon the rate of diffusion of molecules through that solvent. Okay, so and that rate of diffusion depends upon the hydrodynamic radii. Okay, so basically, these are connected to each other. Fluctuate. We have time dependent fluctuations. That is basically something which we can observe. Now, why these fluctuations are taking place? Because the diffusion of the molecules through the solvent is varying with time. And why it is varying with time? Because the radii is, sometimes it becomes small, sometimes it's large. Small and large means sometimes they aggregate with each other and they become quite a large a radii. Okay, it is not atomic radii, it is hydrodynamic radii. Many atoms, many molecules, sometimes they come together, they cling to each other, they form a macromolecule, and uska jo radius hoga उसे हम बोलते हैं hydrodynamic radii. So if the radii is large, it will diffuse slowly. The movement will be slow. When the diffusion is taking place slowly, the fluctuations will also be slow with respect to time. So if the fluctuations are fast, that means that the rate of diffusion is very fast. That means the hydrodynamic radii is quite small. This hydrodynamic radii, this is also called as Stokes radius. Okay, now we have a set of three equations with the help of which you can calculate the radius, the hydrodynamic radius. Let me go in the reverse order. Now the hydrodynamic radius is the equation that is Stokes-Einstein equation. It says R is equal to kT upon 6 pi eta into d. K is the Boltzmann constant. T is the temperature in Kelvin, and pi, of course, you all know. Eta is the solvent viscosity. D over here is something which you don't know. Okay, so that means if we have to calculate the hydrodynamic radius, I need to calculate D first. So what is D? D is actually the diffusion constant of a particle, which is given by T upon Q square. That is, T is the decay rate of that particular substance, and Q is the magnitude vector, which again is given by 4 pi n naught upon lambda naught sine theta by 2. Okay, so n is the solvent index of refraction, that is refraction index it is. Lambda naught is the vacuum wavelength of the incident light, and theta is the scattering angle. So scattering angle, you can see that it comes from this theta over here, that at what angle, from the expected straight line, at what angle you were actually calculating or recording the light rays coming, the scattered rays coming in. This angle between the two, this is theta. This we are going to use. Okay, so we know these constants. If we know theta, we know the refractive index, we know the wavelength of light. We put it into this formula, we get something called a magnitude vector. This magnitude vector, I put it over here in the formula, I get diffusion constant. And this diffusion constant, finally, I put it in the formula of hydrodynamic radius. And this D, which I get over here, this will actually give me the hydrodynamic radius of the macromolecule which is present in my solution. Okay, so like this, you can actually find out the size profile of a solution, that what kind of radius molecules are present in your solution which are giving rise to this scattering. Okay, so we can say that DLS is used to characterize the size of various particles, including proteins, polymers, and carbohydrates, nanoparticles, etc. Then you can also have stability studies. Okay, periodical DLS measurements of a sample can show whether the particles aggregate over time by seeing whether the hydrodynamic radius of the particle increases or not. This is what I told you for cataract onset. Okay, with time, are they coagulating together? If they are coagulating together in that solution, that means over the time when you apply DLS, you will get a higher value of hydrodynamic radius. Okay, if particles they are aggregating, there will be a larger population of particles with a large radius. So R will start increasing with time. That means there is coagulation or aggregation taking place, and in cataract that actually shows. If you see that phenomena taking place in your eye fluid, it shows that the cataract is about to start. So in some DLS machines, the stability depending on the temperature can also be analyzed. Okay, basically you can see that as the temperature rises, is this Brownian motion, is it increasing, is it decreasing? So that time fluctuations that you observe, are they increasing with time or are they decreasing with time? All that is called stability analysis, whether the substance or the solution which is under consideration is stable at various temperatures or not. So all these kind of studies we perform, with the help of DLS technique. And this is very, very important when you are studying various kinds of biological fluids coming from human body. You have to analyze what kind of, fluid is being produced in the body. If you have to analyze the composition of some fluid and see whether there is, some unwanted infection or not, all these kinds of things you can actually perform with the help of the DLS technique.